In this lesson, we're going to look at gases as they're taken through what are called thermodynamic cycles. We're going to allow gases to expand outwards, as this kind of purple piston is supposedly doing here, or we're going to compress gases inwards. So that involves work, which is one way we've seen we can transfer energy in and out of a system. We also need to look at heat, which is the other way. And ultimately, as we look at these systems, we're going to try to figure out what's going on with all three quantities and use that to figure out whether the system is gaining or losing energy. So what we need to do is figure out if this graph tells us anything about the work that's being added to the system. So I want to go back to the idea of work. And from your last year's class, you probably remember that work can be expressed as force times distance, or the dot product of the force and distance vectors. And if they're at an angle to each other, it's FD cosine theta, but we don't need to go there today. Pressure is force divided by area, leading to either pride in our AP class or pride in Pennsylvania, whichever you like. I kind of think the second one is going to be easier for what we're going to do next. We'll plug in. Work is equal to PAD. So what could area times a distance be? Well, if you think about like a cylinder expanding, and it kind of expands out to a new place, we'll call that delta D. Maybe I'll label that delta D. That cylinder is pushed out. It's now enclosing a new volume. So area times delta D, that's like area times height. That's where we get this equation, work is P delta V. Notation for energy transfers can always be difficult, and it has to do with the fact that you have two perspectives here. You have energy being transferred from one place, in this case our gas, to another place, the surroundings, or vice versa. So what I just talked about was an expansion. I talked about this gas expanding outwards. The gas puts an outward force on the surroundings, always. If the gas expands and this piston moves outward, we have a P delta V, and that means the gas is doing work. So energy is leaving the gas. So if we talk about the work done by the gas, it's a positive number. But if we talk about the gas itself, it's lost energy. The work done on the gas is negative. The opposite's true if you compress. We have a negative delta V in this case because force and distance the piston move are opposite directions. And that corresponds to work being done on the gas by the surroundings, a positive number. These negatives cancel. So the work done by the gas in that case is negative. So this can be wicked confusing, and we just need to make sure we're paying attention to exactly what we're talking about. In the following discussion, I'm going to talk about the work done by the gas, and I'm going to be talking about energy being transferred away from the system. If we look on the little thermodynamic cycle I just made, I want everyone to think for a second. I've got process 1, process 2, and process 3. And I want you all to think about one of these processes can't do work. Cool. Process 1 can't do work. And what is the reason for that? Good. So delta V equals 0. So So what is actually happening with process one? We've got essentially pressure building, but volume's not changing. So what could be something that would cause that? So this would be like us heating something up in a sealed container. What we call that is constant volume. I'll put the word up, but again, you're not responsible for this, but just in case you've seen it, isochoric. What do we do at processes 2 and 3? They clearly both can do work. And it's not obvious how to get the work from this graph. And this is one of those places where I feel like teaching physics without calculus leads to unsatisfying explanations. So you're just gonna have to live with this one, and I apologize. Work is the area under the curve on a PV graph. Now, some of you guys who've had calculus would recognize I'm talking about taking an integral here. So we have to look at processes 2 and 3 separately. So for process 2, and notice on process 2, what's not changing? So that's constant pressure. Anyone remember a word for that one? That one's more common, isobaric. So for process 2, what's the work? It's this. So how are you going to get that work? You're going to take its integral, but that's easy for a nice geometric pretty shape like this. You'll just do length times width. Integration is just finding areas. The reason we have to learn calculus formally is that some areas are wonky. Rectangles are not. So process 3, and that doesn't have a name because that is actually not any sort of special curve at all. We're going to see that for the other things that are constant, like holding temperature constant or not putting any heat in the system, that what you end up with for process 3 is actually some sort of curve. But the reason we're using a linear process 3 in this case is without involving calculus in here, we can't deal with any sort of complicated geometry. So process 3, not special. Sorry, process 3. It also has an area under the curve for finding the work it does. So that is the area of this beautiful trapezoid, like that. Again, super important if we're trying to compare process 1 and process 3 to know whether we're talking about work done by the gas or work done on the gas. In process 1, our volume got bigger. So if we're talking about work done by the gas, that was positive work. In process 3, our volume's getting smaller. So if we're talking about work done by the gas, that's negative work. The opposite would be true if we were talking about work done on the gas. But at the end of the day, these two works, we're not adding them together, we're subtracting them. That's process 2. Process 2 does this much work. But you also have process 3. Process 3 does the work under its curve. So what's the work that the whole cycle does? If this is all that 2 does and this is all that 3 does, you basically just subtract these two areas from each other. So the work done by the whole cycle is the area of this triangle. It's important to understand that our entire discussion on these graphs has to do with work. But if we want to talk about changes in internal energy, according to the first law of thermodynamics, we have to consider not just work but also heat. So how do we get at heat from these? They don't tell us about heat directly, but we should remember that internal energy, according to those equations on the right, depends on one variable alone, temperature. So we can use our understanding of ideal gases to take a look at these thermodynamic cycles and see what's going on with temperature. So you can see that temperature depends on pressure and volume. And as we go around a cycle, we start with a pressure and volume. We come back to that same pressure and volume. So we don't have a delta V or a delta P, in which case we can't have a delta T. So that means we must end up back at the same temperature we started with and with the same internal energy. So that's how we can figure out what's going on with heat, even though the graph doesn't directly tell us anything other than work. Any two processes that start at one point and end at a different point, doesn't matter what path they take to get there, they will have the same change in internal energy.